Hello, I'm Dr. Paris von Lockett, and today I will be talking to you about how to solve the plate with a hole problem using some hand calculations and using some correlation tables or some equations on stress concentration factors. Important to remember that this particular method can be applied to anything with a notch or with a hole, and if you're looking at these problems with some similar geometries, we can go about applying these methods to those as well. Okay, so this lecture focuses on solving by hand the problem of a plate with a hole in it. Topics for this lecture: solution of this problem, and importantly, using net cross-section properties to compute displacement and stress. We'll run through how to do that. After this lecture, it's important that you can use Norton's stress concentration charts. I'll give you one here, and we'll give you some later for a later assignment to determine the stress concentration factors. You can compute the displacement and maximum stresses in the plate using these methods. And finally, that you understand that this concept of reduced cross-sectional area can be applied to other geometries that are similar. So yeah, the notches reduce the cross-sectional area, the hole will reduce the cross-sectional area, and as long as we have the right table or the right correlation equation, we can apply the same methods. Okay, so what we'll assume here is that we've got the problem as shown below. We've got a plate 6 inches by 2 inches by 1/4 inch deep. It's got a hole in it with a diameter of 3/4 of an inch. We'll assume the hole is perfectly centered in the plate. We'll also assume that our 300-pound loads acting left and right are not point loads, but that they're distributed over those faces such that they don't themselves cause stress concentrations. First things first, let's find the nominal stress that would exist in the sections that we're dealing with. So how do we find this? The nominal stress developed at the smallest cross-section in the plate. So what does this mean? Well, we look above and below the center of the hole. We look at the material that's actually there. So here and here would be the only place we'd have material that can resist this load at the smallest point, and we calculate what the stress is at that location. We call that, again, our nominal stress. So stress nominal is P over A, straightforward. We have our 300-pound load divided by our depth, which is 1/4 of an inch, and now the only remaining part of our height, which is 2 inches minus the whole 3/4. So that yields us 960 psi. Okay, so how do we go about calculating this maximum stress? Well, we can look on tables produced by Norton and also some other folks on how we compute the stress concentration factor. And what we're shown here is that we can do this if we know our particular geometry. Here's a representation of the geometry associated with this particular correlation. We've got an end-loaded plate. It's free on other two edges. There's some diameter d for our hole, some width w, and some height h. So this does represent our geometry. And as long as our part falls within this ratio of d over w less than or equal to 0.65, we could follow this equation, or we could pick up our numbers off this chart. So if we calculate our geometric factor, we get 3/4 over 2, which is 0.375, which does fit the value that we need. Since this does fit the value that we need, we can then go back to our chart and trace out the line for our correlation or our fit, find our 0.375, look at the intersection, and find out that it's just below 2.3, or plug into the equation here on the right and find out more specifically that we've got a KT value of 2.27. Great. Then we can calculate our sigma max as our nominal stress, which we just calculated, times this geometric stress concentration factor, 227 times 960, and we'll get 2180 psi as our maximum stress. So there we go. The maximum stress in our plate, 2180 psi. And if in addition we wanted to calculate or estimate, I should say, the maximum displacement, we could do this by using our classical 1D approach, assuming this is a 1D bar. In that case, delta is PL over EA. If we remember how to take our load divided by the area to get our stress, take our delta, which is our displacement, divided by the length to get a strain, and then we can scale all that by sigma is equal to E epsilon. We can rearrange that to get this equation here. We can look for a lower bound. Our lower bound, we look at the right or left edge and measure from the center of the plate, considering the full width, meaning that, yeah, we're going to assume the whole thing is acting here or the whole thing is acting there. So we can just take our load, 300, times our length, 3, divide by 10 times 10 to the 6, if we assume our modulus, and then 2 times a quarter for the area, and that'll give us 1.8 times 10 to the minus 4th inches. Our upper bound from our reduced section, now we're assuming our whole is acting, so we only have this area and this area in our reduced section. Our PL over EA still has 300 for our load, 3 times our length, 10 times 10 to the 6, again for our moduli, and now that area, which was, or I should say that height, which was a full 2 inches, is reduced to 1 1/4. We multiply that by a quarter, and we're left with 2.88 times 10 to the minus 4th inches. So we have upper and lower bounds. We can, for the sake of this argument, just take the average of those. The average would then come out to be 2.34 times 10 to the minus 4th inches. And that's enough of analysis for this plate. One thing I do have to point out here is when we use this length of 3, what we're looking at is just half of the length of the plate. Since we're looking at half of the length of the plate, what we're assuming is that this half is going to extend by either 1.88 or 2.88 upper and lower bounds, or this average 2.34. And if we look from the middle to the left, we'd have the same delta 2.34 because it's symmetric. Overall, it would change length by 2 of these, but what you'll see in our SolidWorks simulation is that we're going to end up only modeling 1/4 of the plate. So this top right quadrant, because of that, we're only concerned about the change in length of this section from the middle to the end, which is why we use this length of only 3 inches for half the thing. Well, thanks for watching. Hopefully you've learned a little bit about how to go about calculating these stress concentration factors, how to apply those to find maximum stresses, and then how to sort of wrap it all up by finding the estimates of the displacements from a lower and upper bound in a plate like this. Please realize that if we have the right table from Norton or some other source that tells us for a particular type of notch geometry that we have, we can get our stress concentration factors for that particular geometry from some different table. And then we can still use our ideas of reduced area to find the section properties, to find the nominal stress, and then we'd use our new KT to actually scale up that stress, and from there find what that maximum stress would be. All right, thanks. Take care. Thanks for participating, and we'll see you in the next lecture.